Okay, so today is the fourth lecture, and I'd like to continue what we ended last time. So what I explained last time was this relatively general existence theorem where you're given, so it's in Rn plus 1, and then you're given capital N domains. Let's just stay with maybe 01, E02, and E03, and E04. And that type of open set, and I explained this condition I think clearly, and we had this, this is given as complement. And basically, what we assume is that for simplicity, this is finite and also it's rectifiable. Okay, so that's a rectifiable count. So given this basically initial surface, I'd like to construct the mean curvature flow starting from this, okay, as a Brakke flow. So the basic scheme, okay, so today and next time I'd like to somehow give an outline of the proof. Okay, and also some highlight some of the computation, which I think is somewhat very interesting. So the basic idea is to first, okay, so first what we do is we first approximate, we construct first so-called time discrete approximate flow. Okay, so you don't construct right from the beginning the continuous family of measures, but you construct a sort of a constant, piecewise constant approximate solution. Okay, so first, well, just very, so you construct a time discrete. So really, it's like a numerical scheme in some sense. You know, when you construct when you do a numerical scheme, you don't do it for continuous time, right? You have some time grid, and you sort of construct step by step, right? That's exactly what we do here, theoretically here. Okay, so time discrete approximate flow, sort of mean curvature flow, approximate sense. And after you do this, okay, so this part is probably what I can tell you, actually. But after you construct this, you take a limit, and you show that the limiting object is a Brakke flow that you want. Okay, so that's a basic like scheme of this. Okay, so then take a limit. Okay, take. So basically, you have this times sort of a time grid size, which I usually write this as delta t. Take this going to 0 and show the limit. Well, limit exists and is a desired Brakke flow. So it's really, in a way, very constructive, which is somewhat different from, say, just minimizing, you know, the area, for example, which is traditionally done in a solution of the plateau problem. But by the way, so I don't do the case where you have a boundary, but we have also results that you can fix the boundary data. Okay, so we can actually solve the plateau problem by this scheme. Okay, so, but that part is a bit more technical, so I don't do that one. Okay, so now, so basically you, let's see. So let me start. Maybe just So for each j, which is a natural number and which goes to infinity, we fix a time grid size to be, let's say, delta t of j. Okay, so that's a number which goes to 0, but for the moment it's a finite number. It's very small, and so the idea is, as I just said, basically you start with this initial, sort of partition. This is really, you think this as more like a partition of Rn plus 1. Yeah, so that's really a partition. Of Rn plus 1 by open set. Okay. And what I do is actually I kind of move these partitions step by step. Okay, so starting from this, I construct the next step, which I may say, and also, so I just omit the index j. Okay, so because so for each fixed j, I do this. Okay, so you just construct E and so forth, delta t and so forth. Okay, so maybe I'm just so that these guys is also these guys are also partition. Okay, over and these are each a partition of Rn plus 1. So you just mentally you should have the in your mind you have this picture that you have this partition and it's moving little by little each step. Okay. Yes. Yes, exactly. Well, actually, but well, at the end, actually, some of them may become empty set. Okay, so I'm writing this, but maybe some of them might be empty set. Well, by definition, these guys are not empty. Okay, so these are not empty, but at some point, typically, yes, actually, some of them become empty set. Yeah, thanks. That's a good point. Yeah, yes, and so now for each step, this guy, each step actually is composed of two. By the way, this result is in detail described is with my work with Kim, and this is mainly described with my work with Kim and myself. I think that's 17. Yeah. So and also some of the improved version of this is described with my work with Stewart. 24 maybe. Okay. So the detail can be found in this paper if you're interested. Okay. Now this each step, in fact, has sort of two operations. Okay, two operations. So this part is a bit. I think this part is really creative. I think about Brakke's work, I must say. I mean, I wouldn't be able to think about this at all, really. So, so this part has two operations, and one is so-called this Lipschitz deformation operation. So maybe I should say. And the other, so the other is I call it as a motion by smoothed mean curvature. I'm taking this word from Brakke's book, actually, mean curvature vector. Slightly misleading, but so going from this 0 to 1, there's two operations. Okay, so it's not just one operation you do, but two operations. Okay? So, and right, so now I'll I think next time I probably will do this explanation, but today I'd like to mostly work on this one. Okay, so yeah, so today I'd like to discuss this part, okay, mostly. And so the challenge here is that, not that the challenge is that, well, okay, maybe we just need to do one step, of course, because the rest, the next step is the same, okay? So just think this first step. And, okay, so the challenge is that, well, now this initial data, which is just country and rectifiable, that's all, as far as the regularity is concerned, that's all, you know, there's no, like, differentiability assumed. And to compute the mean curvature vector, of course, classically, you need the C2 regularity, for example. Of course, we don't have that much of the regularity. So the challenge is actually, given this set, which has very low regularity, you have to come up with some sort of analog of the mean curvature vector in a suitably approximate sense. Okay, note that even if you know about varifold, note that this guy even doesn't have a first variation bounded, for example. Okay, so if you know about the varifold, okay, if you don't worry about it. But there's no regularity with this. So the first challenge is to come up with some suitable notion of the mean curvature vector. Okay, so this I have to explain this, but now, to evaluate the all this approximate quantity, one introduces this class of test function. Which definition is 8. Okay, I'm actually doing lecture from some notes I did the lecture on before, and so I'm skipping a lot of stuff. So the numbering may not correspond to in order. So, but define the following. So this is for each fixed j. Okay, we define this so-called, I call this script aj. Usually, I'm not so sure how to call this. This is the class of test function, which is C2 on the entire space, and with the following property. Phi is strictly positive and bounded by 1. And at each point, the gradient of phi, this is pointwise condition, is bounded by j times the function itself. And also the second derivative is also pointwise bounded by the function itself. Okay, so that's function for all x. So this function is maybe looks slightly strange because you know, the gradient and the second derivative is bounded pointwise by this way. Now j is a huge number, so when j is large, this becomes less and less restrictive. Okay, and well, okay. So first, we know that phi x equal to 1 is in this class, obviously for all j, because 1 satisfies all these, of course. And also note that for any, and also for any phi, which is C2 compact, say, which we want to use this as a test function at the end, but and the phi is non-negative. Let's take any arbitrary C2 compactly supported function, which is non-negative. Then it's not so difficult. Well, actually, it's easy. Yeah, sorry, less than 1, I guess. Yeah, strictly less than 1. Then, in fact, we can, there always exists some large j such, given epsilon, okay, so given any epsilon, which is small, there exists always some large j such that this phi plus, maybe phi plus epsilon, okay, so that's a function which you lift the phi a little bit, a very tiny amount, belongs to script aj. So whenever you have some C2 compact supported function, if you just lift a little bit, and J is huge, J is very large, then you can make this belongs to this AJ, because it's very easy, because obviously, epsilon is, okay, so now I'm assuming epsilon is very small, so that this is less than or equal to 1. All right, so I shouldn't say any epsilon, but sufficiently small epsilon, I guess. This function is going to be less than 1, and also, of course, strictly larger than 0, but also the gradient of this function is obviously equal to the gradient of phi. Okay, and okay, maybe I should put x, but and then this is bigger than this is less than equal to epsilon over 1 times sorry, I guess maximum of nabla phi times phi x plus epsilon. Okay, so that's sort of trivial inequality. Okay, so just because phi is bigger than or equal to 0, so this part become obviously bigger than or equal to 1, and of course you're taking maximum of nabla phi. So similarly, of course, maybe I don't have to do this for the second derivative, but you can see, obviously, if this number is less than j, then we have the, this phi is going to belong to this class, okay? So the point is, in some sense, given any test function, which I like to, use at the end, the whole thing is really about the estimate. So I want to use this kind of test function at the end, but this kind of function can be, in some sense, approximated very closely by any function in this class. Okay, so that's what I claim here is that in some sense, so the idea is that this union of this AJ is more or less like C2 compactly supported function. Okay. So I want to use this class. Now the reason that this class is introduced is somehow now it's very not so clear, but this function has a very nice property in the sense that maybe in the next lemma, I'll tell you, lemma, very easy lemma, is that for phi in script AJ, we have this phi of x is less than or equal to phi of y times exponential function of j times x minus y. Okay, so this is true. Proof is just one line, really, because if you look at the log of phi, this is obviously less than or equal to phi divided by nabla phi, and that's bounded by j. Okay, so if you and then by mean value theorem, I guess, yeah, and it gets you this one. Okay, no problem. Yeah, this is bounded by j. Okay, so this gives you this estimate. So note that this implies that this phi has this very interesting property, which, by the way, I think I probably just put this number 14. I'm sure that numbering is strange, but let's put this 14. So what I like to point out is, so for x minus y, that if the distance is smaller order of 1 over j, then if the distance is much smaller than 1 over j, then this function behaves more or less like a constant. Because it only, if this is much smaller than, very close to 0, that means fx and phi y is basically compatible. So that means, in this case, phi x over phi y is more or less 1. So phi behaves like a constant in a small scale. So what I'm doing here is actually introducing some scale where this phi is more like a constant. Okay? But as I said, if you look at the much bigger scale, length scale, then this function can behave more or less like a compactly supported function, nice function. Okay? So that's interesting. Class. Okay. So as I said, this class is really, you can approximate this C2 compactly functions arbitrarily as long as J is large enough, but at the same time has this length scale where phi looks really like a constant. Okay, so this now I think you need to see a bit more further things, but I need to define this. Okay, so the next thing is I define this the usual heat kernel, Gaussian, to be this is some constant times let's see here, I don't know, maybe just okay, x divided by 2 pi epsilon to the square and plus 1 times exponential function of minus x squared. Okay, where this eta is a function which is a really cutoff function, is a usual cutoff function. Say it's 1 near the origin and then become 0 on somewhere like 3 over 4 or something. Okay, so it's eta is a cutoff function. Okay, so eta s is 1 on s 1/2 or something, and 0 for s bigger than 3 over 4. Okay, and C epsilon is chosen so that this integral on Rn plus 1, this is equal to 1. Okay, and note that if you don't have this cutoff and this constant, it's really a usual Gaussian. And this, without this guy, if this is 1, then this is a usual Gaussian, and the integral of this on Rn plus 1 is equal to 1. Okay, so I'm just cutting off, and then there. Well, and I'll be interested in the case where epsilon is very, very small, of course. So it would be like spike at the origin, and error of cutting this guy, cutting off, is really exponentially small, actually. So this number is very, very close to 1. Okay, this constant. So you can easily check that this goes to 1 as epsilon goes to 0. Okay, anyway, so that's a usual, well, okay, so you might say it's a modifier. Okay, so you have various kind of modifier. But here is, I'd like to use this modifier, this particular modifier, which turned out to be very useful, actually, at the end. Okay, and also, yeah, as I said, this delta, this guy, as epsilon goes to 0, converges to basically a delta function. Okay, delta function. Okay, so now, so I need all these guys, and so the next thing is to show So the introduction of the this approximate mean curvature vector. But before I do this, maybe I should point out a few things. So first, you see, we would be having this gamma 0, or so which is closed country and rectifiable. So let's actually just note, let gamma to be, just denote this by gamma, okay, just for denote. Okay, so I'm just interested, okay, well, I think it's clear, yeah. So given this gamma, I would like to have some notion of mean curvature vector, but just as a motivation, first, assume that assume for the moment that gamma is actually C2 n-dimensional surface. Okay, and then recall that in this case we have this formula that's 4. I put the number 4, which is that we have this formula that divergence of this Tx gamma of Gx Hn of x is equal to this gamma of H gamma dot G x Hn x. Okay, so that was a formula we had before. So in the C2 case, of course, we have this formula in a classical way. Okay, so it's just a classical object. Now we use this as a motivation to define a smooth mean curvature vector. Okay, so what you do is that, okay, so use this as a motivation, and it actually works very nicely, almost like you'll see some of the computation today. But so what we do is we use Gx, this vector field, to be the following. So I put this Gaussian on the ice component. Okay, so let's see, x minus y. So y is fixed. Sorry, I think I said, yeah, okay, so fix y. Okay. And then I look at this vector field, where this is i's component. Okay. And use this vector field as a test function in here. Then what you have is that the right-hand side of this formula is going to be, yeah, just you just use this. So that's just gamma of the i's component of this mean curvature vector, which I write this as I, and you have this just by substitution. Okay, I hope it's very clear. I'm just put this vector field whose i's component is Gaussian. Just write out what we have here. That's it. And what we do is, we do the following. So you just let us do the following. So you divide this right-hand side by this quantity. Okay, and which is nothing just but this H gamma x I Gaussian Hn divided by epsilon plus x minus y dh x. Okay, I'm just writing out what's there. And note that if gamma is nice and smooth, well, let's see. What we have is that if y is in the surface, then what happens is that you see this Gaussian is concentrated around y, of course. Okay, and assuming that everything is smooth, h is more or less continuous nice function. So this would be roughly, well, I guess maybe I should this way. This would be roughly, okay, so just assuming this is constant, so that more or less this function is going to be the value at y, and then you have the rest. Divided by epsilon plus gamma, the same thing. Okay. Now, also note that if y is in gamma, this is going to be more like well, this is like n plus 1 dimensional Gaussian integrated over the n dimensional surface, more or less. So this is behave more or less like 1 over epsilon. Okay, you can sort of think of that because you see this is n plus 1 dimensional Gaussian. So if you integrate over n dimensional subspace, I mean when epsilon is small, this is more like integrating in a tiny neighborhood of this gamma near y, and you can check that should be like behaving like this. Okay, I think that's correct. Yeah, basically you do change a variable. And yeah, you're left with only one epsilon here. So anyway, so the point is, so this blows up, but these guys are the same here. Okay? Now this epsilon can be ignored because this is huge. Okay? So this converges to basically h gamma y of y. Okay? I hope this is clear. Yeah, and epsilon goes to 0. This quantity converges to this mean curvature vector at point y. Okay? So that's fine. This right-hand side is fine. Now, you can actually use this as a motivation to define the mean curvature, approximate mean curvature, using the left-hand side. So the point is here, so motivated by this, for gamma, which is rectifiable, okay. And by the way, this can be done for any dimension. It doesn't matter if it's n-dimensional. We can define, motivated by this, so definition of 9 is that we define basically the this vector field stick into this guy. Okay. Now notice that this side is well defined for rectifiable set. Note that this is, because you see this tangent space exists almost everywhere for rectifiable set. So you can actually define this quantity, and you can integrate over this gamma. Okay, so this side is in fact well defined for rectifiable set. So using that fact, I define this h tilde of epsilon gamma of y, i's component of this. Okay, I is from 1 to n plus 1, to be defined as basically minus of gamma of divergence of Tx gamma of this, the vector field that we just saw. So x minus y and dhn of x, okay, divided by, okay, so note that we have divided right-hand side by this denominator, so we just do the same things on the left-hand side too. Okay, so that's just a definition. Of course, this is ice component. Okay, I hope that that's clear. Yeah, so this is supposed to be, if everything is nice and smooth, this quantity converges to the mean curvature vector. Okay, but if not, then you may blow up. Okay, but whatever the case, this is a well-defined quantity for a rectifiable set. I hope that's clear. Okay, so now, okay, so yeah, by the way, so if it's in Y, it converges to mean curvature vector, but sorry, maybe I should have said that, mentioned also. If Y is not in Y, sorry, Y is not in gamma, then what happens is that, yeah, I should say that. If this is the case, then this guy, well, if Y is off the surface, then this quantity basically is a Gaussian. So if you're away from the sort of a singular point or the origin, it decays exponentially fast, right? It decays exponentially fast, and since you have epsilon on the bottom, this converges to 0. Okay, exponentially fast actually. So if Y is not gamma, then this quantity, right hand side, converges to 0. Okay, exponentially actually. So it's a nice sort of function which really concentrated on the gamma, but otherwise it becomes 0 very fast. Okay, so that's one guy, and yeah, I think I should put number here. I put 15. Equation number 15. And also another one, which will be clear why I'm doing this, which is another one is, in fact, we want to consider this one, again, for I from 1 to n plus 1. This is defined as the, so let's see, we had this tilde there. The reason I had that tilde is because I want to do another modification. Oh yeah, this would be, I guess y. Yeah, y is there already. X minus y, h tilde of epsilon gamma of x dx. Here is a Lebesgue integration here. Yeah, okay. So why I'm doing this will be very clear soon. But I do another modification, okay, of this H tilde. And also note that H tilde itself is actually smooth vector field. Okay. Note that both H tilde and H both actually C infinity vector field. By the way, so these are the components I consider this as a vector. Yeah, so it's a vector field on Rn. Okay, because after all, that's when you differentiate, the differentiation falls on the y. And with respect to y, it's actually smooth. So yeah, okay, and it's well defined. Okay, so let's see. So lemma, first lemma. Yeah, so maybe just to fast forward the story, what I do is I use this guy, this vector field, as a substitute of mean curvature vector. Okay, so this is a vector field that you move the surface. Okay? But of course, you have to have some estimate to make sure that everything is fine. So this lemma is a bit technical, but just first I'd like to point out that this vector field has this property that this and epsilon square force of nabla H, this is bounded by some constant depending only on dimension, and 1 plus epsilon times the n-dimensional surface. Okay. Equation number 16. So this vector field actually eventually, well, blows up. Actually, after all, it is more like a concentrated on the surface. So, gradient, of course, has to blow up. But there is certain control, at least in a controlled way. Okay, and this is proof is very easy. Just so this I like. Okay, so for the people who wants to get a credit, please do this as a homework. Is that 4? Yeah, I guess 4. Yeah, 4. So, but I'll do it. I'll just write the results, and so this is just fill in the detail. Okay, so that's a homework. So this tilde, first you compute this is after all, just by definition, right? So you look at that one pointwise, and so divergence is really nothing but just the gradient, but projected to the tangent space. So you can check that this is less than or equal to gamma of nabla phi, basically, and epsilon of x minus y, dhn, divided by epsilon plus nabla epsilon dhn. And you can check that this differentiation has, I think, only problem is you have this test function, cutoff function, so you have to differentiate this guy and also this guy, okay? Differentiation of this guy is actually, the only place where this is non-zero is a bit away from the origin, okay, because of this cutoff function, okay? So away from the origin, where the gradient is non-zero, this guy is actually very small. It's exponentially small, actually. And so you can actually bound this appropriate way. And also the differentiation of this guy gives you epsilon square, outside, okay, because you have this epsilon square. So in the end, you can show that this comes out to be some constant divided by epsilon square plus Cn and epsilon times the n-dimensional surface measure. Okay, so something like this. So I think this is good enough. Okay, so please check this. Okay, check. And in fact, I don't think there's more detail in my paper, but I think maybe there's some detail in my paper with Kim actually about this point. Okay, so that's, if you're interested, yeah. So this gives you, this is for H tilde, but for H, you have even the better ones, like you modify this again, so you have the same estimate basically, for H, yeah. So I think that's for people who knows, it should be clear. And also the gradient of H tilde is the same, more or less. This is, again, you can check that this is less than Cn just by following the same type of computation. Epsilon cube Hn of gamma. Okay, so that's about it. So of course, again, H is the same estimate. Yeah. So right. Okay. So I hope this part can be quickly done. And let's see, maybe I should, at this point, maybe, yeah, okay, maybe I'll just continue and stop. Lemma 3. Next lemma is maybe I write this and finish. And this is the reason why we have this double sort of smoothing. So the following formula holds. This one's kind of nice little lemma. This is equal to minus of it's h tilde square times phi. Let me explain this. Yeah, I forgot to say that I want to use a notation that, okay, every time I don't want to write this, so let me write this as, well, since this is like a convolution, so let me write this convolution of Hn restricted to gamma, okay? So I write like this. This is a function, actually. Okay, so when I write this, it means this guy, okay? So I hope that's clear. Yeah. So let me use that notation. Yeah, and let's see. Hn gamma plus epsilon. Okay, so that's number 17. Okay, so this is a nice, very nice formula. Okay, I think it's very not so clear what this really is, but note first, this is an approximate formula of the following. So remember that the number 4 was this formula, that gamma of divergence of G is equal to minus of H dot G, right? Now, this was a formula for 4. Now, if you use G to be equal to H, okay, so just let G to be equal to H, you get this formula. You see that, right? If you just, formally put H into G. Well, of course, you have to assume higher regularity in this. Of course, you have to have surface to be C3, for example, more or less. Now, this formula is sort of analog to this. Sorry, maybe I should say this is the analog of this formula in some sense, because note that here is sort of approximate mean curvature vector. You're taking divergence, integrating, so it's exactly like this, but except it's approximate. Okay? And this right-hand side has a minus sign, and here's a square, but actually H tilde, not H, okay? H tilde squared. And note that this is really like, if you take epsilon goes to 0, this is concentrated, this become more or less like Hn restricted to gamma. So it's really like integrating over the gamma. I hope you see that, yeah? So this formula is really analog to this one. And then this formula, just follows somewhat nicely with the way we define this. So, and note that this formula is very important later because we are moving the surface by this approximate mean curvature vector. Then when you do that, you have to make sure what is the rate of change of the area. And this left-hand side basically tells you the rate, like how things is changing, how the area is changing when you move the things by h. And that's given by basically this formula here. So this really tells you that if you move by this approximate mean curvature vector, you are really reducing the area. Okay? That's sort of the importance of this formula. Yeah, I guess so. I think you probably don't get the right formula. Yeah. Yeah. You'll see right away actually why this is. I mean, it's after all, it's an equality, so it has to work out nicely, right? Of course, yeah. Okay, so let's see. This could be like an exercise problem actually, but since don't have to make this into exercise. Yeah, well, this scheme is actually quite general, and this works even for more general bifold. And so, yeah, I feel like this should be used more, but I don't really know any other places that this is done. Yeah, my paper with Kim, it is written for more general bifold, so but yeah, maybe it's easier to see this way. Instead of looking at this as a bifold, more like this is very easier to understand, I think. Okay, let's see the proof of this. This follow really from the definition more than anything. So it's really that I define this so that it works. So proof is just writing down the definition. So the divergence of H. Okay, so that's and is equal to if you write what this is gamma of, well, divergence is really the okay. So let me use Einstein convention. Tx gamma ij. So this is, you think this as a sort of projection map to the tangent space, of course, and differentiating H epsilon gamma, ith component of this, and then differentiating with respect to j. Okay, so that is what it is. Okay, so I hope that's clear. Yeah? That's just the definition of divergence is precisely this. And then, right, and then also note that this guy is the one that you get by modifying H tilde. So you can again write out this modifying. You write out what this is. So this would be Rn plus 1. And then you're differentiating, but you need to differentiate with respect to Gaussian, of course. So this gamma xj and x minus y, and you have h tilde epsilon gamma and y. Okay, let's see. You have this i's component, and here's a dy and dhn of x, right? And then you do a change of order of integration change. Yeah, Fubini theorem. Fubini. So you get integration over Rn plus 1 is a gamma of is Tx gamma ij, and if just writing out the computation, okay, x minus y dhn x and h tilde epsilon gamma and I dy. Okay. Now what we have here is that this one, let's see, this one, I guess. Note that this part is really a divergence of this, note that you're differentiating this and then projecting to this one. So if you think about this, this is nothing. Let's see, what do you have here is let's see. Yeah, you can actually write this. Maybe first I say that this is divergence of this 0, 0 gamma epsilon. Okay, that guy. This part. Okay. This is divergence of this particular vector field. Right? I'm just following the definition. Yeah. That's what it is. So you write, you see, after all this was integration of this. Maybe I should write like this. After all, this is equal to, actually, it's a minus of, this is, after all, this is minus of h tilde epsilon gamma of y of the I guess, times this bottom guy. Okay, I think this is, okay, I defined this quantity before by this divided by this weight, right? So at the end, this become nothing but just Rn plus 1 minus of H tilde epsilon gamma y I and times epsilon plus this modifier and H tilde epsilon gamma y I d y. Okay, so that means, you know, this of course H square, so that's minus H tilde epsilon gamma y square times gamma plus epsilon. Okay, so that's all. So nothing, you know, mysterious actually once you know the definition, and that's the reason why I did this, you know, modification another times, just to have this duality of sort. Yeah, so that's fine. Okay, so that's nice. Now, actually, but this is not good enough, and actually the next one is more important. So this is the more like you know, integration over all space. But what we need is a bit more sort of localized information too. That is, you know, we want to actually, you know, to get a Brakke's inequality, it's not just that you need to know the total measure, you know, change, but you need to know about the local measure change as well. Okay, so because of that this is not good enough. You need to know more localized version of this. Okay, and that the next one is precisely that one. So this is proposition 9. This corresponds to yeah, a more precise statement you can look at in my paper. 17. Okay, so suppose the measure is finite. Okay, so bounded by m. Then claim is then there exists an epsilon which depend only on the this m and n with the following. Okay, so now suppose that epsilon is the one that appears in Gaussian is less than or equal to minimum of epsilon 0, and here's a little bit technical looking guy, but to the 6. Okay, so compared to yeah, so this will come up later, but I need to introduce a couple of length scale. So one is small scale 1 over j, which is small, but I need to have another length scale which is much smaller, which will be epsilon. Okay, and so a little bit technical, but I'd like to explain this maybe next time a bit more carefully. But so I assume that the epsilon is somehow smaller than this number. Then for any test function phi, which is in this script aj that I described you before, we have the following. We have this estimate gamma of divergence of I h epsilon gamma, okay, and dhn plus Rn plus 1 and phi times h tilde square. Oh yeah, I think I'd like to introduce another notation because I don't want to write this every time. Let me write this or maybe I should say this part. Yeah, this part is kind of long, so let me write this as, it's like a, this one's, let me write this d mu epsilon gamma, okay, just for simplicity, because it's a measure which is really like a n-dimensional Gaussian, n-dimensional measure, but approximation. So let me write, this part as this d mu epsilon gamma. So I using that notation, here is a du epsilon gamma. Okay. This is bounded by epsilon to the 1/4 and Rn plus 1 I h tilde square d mu epsilon gamma plus 1. Okay, so that's equation 18. So that's the estimate I'd like to explain next. Now, this 18, as you can see, when phi is equal to 1, phi equal to 1, we had the previous proposition. Phi equal to 1, that's actually equal to 0. This left-hand side is equal to 0. Okay? So it's a localized version of what we saw before. Okay? So we need a bit more, precise information what's happening in a local, sense. So and again, this is really so the remark is if phi is equal to 1. By the way, phi equal to 1 is always in this script J class. Then we have left-hand side equal to 0. Okay, so and as by proposition 8. Okay, so that's what we saw this already. And again, this is again the formula that you expect, because in equation 4, if we let G to be just a phi times H, okay, in this formula 4, which is integration by parts formula, if we stick in phi H, this left-hand side should be equal to 0, in fact. Okay, it's exactly equal, 0. But here we don't have 0 this time. Okay, because phi, after all, is a kind of test functions, and but interesting thing about this test function phi is that, remember that phi behaves more or less like constant in the scale of length 1 over j, right? That's how we define this test function. So in a length scale of 1 over j, this phi behaves more like a constant, and in some sense, epsilon is much smaller than that number here. See? So in some sense, this phi cannot detect that this mean curvature is an approximate mean curvature vector in some sense. So that's the reason I'm introducing this test function, to get this kind of estimate. Okay. So, and note that also, the other thing is, well, this right-hand side you see, note that here you have the same, same guy here. So in some sense, and also at the end, what we have is that this term is more like is a term which is controlled in some suitable sense in a mean curvature flow scheme. So this quantity is actually controlled at the end. Okay, but with this number still small number, we are in good shape in some sense. That's the kind of story about this. So yeah. So again, as I said, yeah, this quantity is controlled. Maybe I should write that. So at the end, okay, so this quantity is nicely controlled. because in some sense this appears as a dissipation rate of surface measure. So you should know that if you're looking at the gradient flow, there's a dissipation, and dissipation is usually if you integrate in time, it's bounded. It's like yeah. So this quantity is a good term. So yeah, at the end. So yeah. So yeah. Okay. Maybe I should. That's good enough for now. All right. So. And the fact that this part works is actually, it's more like, analytically speaking, it is a key point, I would think, about why this scheme works somehow. You'll see why this part is very important. And it's actually quite ingenious to me. I don't quite understand why this works. It's more like a mystery to me still, after many years. So I hope you can get that feeling also. So let me show you the proof. Okay, so this is very, and actually it's very important that this is Gaussian. That's actually somehow very important. Gaussian. Important here. And somehow this is a unique choice that you can make. Okay, so let's see. So basically, first you just write out again what these guys are. Divergence of gamma of IH. Okay, so you write out again by following the definition. Yeah, actually this part is exactly the same as before, and yeah, we saw the case of phi equal to 1 before, right? So, and I guess I erased it already, but you can just check. Yeah, here I guess we have that still. Okay, so we had instead of h, we have phi times h. So you have phi times h there, and let's see. So you can follow. I think I just checked my notes, and after change of variable after Fubini, you can check that it comes out to be this. Okay, so this. Well, let's see. Ik. I'm just using ik. Ex gamma. Ik, and we have 2 terms now instead. Let me write this carefully. Times phi x ehn x times h tilde dy, and another term that comes from the differentiation of phi. Okay, so maybe you can check this later. Don't want to repeat the same computation. So ik ex gamma ik. Now d phi dxk of x times, sorry, it's quite long, but phi x minus y okay. So you can check the when you have a phi, you have this expression. Maybe it's easier to see that if phi is equal to 1, I think we have exactly the same things. When phi is equal to 1, you just compare. Well, index is a bit different, but otherwise they're the same, right? You see that, huh? It's the same. If phi is equal to 1, But since phi is function, then you have to differentiate this guy this time. Okay, so that's the only difference, right? So please check this at home, later if you like. And the other term is let's see. You just check another one. So minus. I think it's minus sign. Yes, minus phi and h tilde gamma mu epsilon gamma dy. Is that right? Let's see. It sounds kind of suspicious. Dy shouldn't be here. Sorry. So this one is minus. Yeah, I guess what I'm doing is. Wait a minute. That's strange. Dear. Yeah, I guess, yeah, okay, so this is dy integration. Yeah, that's right, dy. So, yeah, it comes out to be a minus of, you just write out again, maybe here's plus, sorry, plus. It's minus of Rn plus 1, and just one a tilde, you write out the inside, ik, and tx gamma, ik, and d psi, and dxk, x minus y. Here is a phi of y, okay, and dhn, x and h tilde of I dy. Okay, and that's, let's call this b. Okay, so you just write out the definition of these quantities and comes out to be like this. So the things you want to prove is that the sum of this is become small. Just to check, yeah, if phi is equal to 1, I think it should come out to be exactly equal to 0, right? Yeah, that's right. I think if phi is equal to 1, you have no problem to get 8 plus b equal to 0. Okay. So the only reason why we have to estimate this because there is this phi. And something that one note is that, okay, so you have a phi here, and then, yeah, and another place one has to look at this part. And also here's y. So these are the places where we have a difference from before. We didn't have these guys before. So now to do so we have these guys as a, maybe I should use that one. So we have to do estimate on these guys. All right, let's see. So let's see how it goes. So the first things to note is that so the error estimate has to be done. Now, first things to check is actually this guy. It's this d phi dxk x can be actually replaced by d phi dxk of y. Well, maybe it's not right. Yk maybe yk of y. So the difference between these guys, let's see, how do I think that? Let's see. Yeah, the difference of these two note that you have this Gaussian after all. this guy, I guess, this Gaussian. And if you are away by epsilon, much bigger distance, x and y are different by distance of, let's say, much bigger than epsilon length scale, then this Gaussian becomes very, very small, okay, exponentially small. So in some sense, you can bound this by constant times. In fact, you can bound this by j times, precisely because of the fact that phi is in aj, script aj. You can actually bound this by more or less like this way, times x minus y. And that's, since this is more or less epsilon, okay, because if it's bigger than epsilon, well, to be precise, actually, maybe you might want to use a square root of epsilon or something. But whatever the case, you can actually more or less, replacing this by this is of the order of epsilon times j times phi, okay? And that's actually good enough to, okay, so detail I'm not going to go, but you can, in this replacement doesn't cause you much of the trouble. That is, you can somehow take into this term. Okay, so let me just, okay, so this can be done. So detail, as I said, yeah, it's in the paper, but that's all the idea. That is, you replace this first by d phi dy k y, and then the error that comes out can be estimated without so much trouble. Okay, because you have this extra epsilon term comes out, and even though you have a j, epsilon times j is still very small because j is much smaller than epsilon is much smaller than 1 over j. Okay, so now the other things you do is you have to interpolate this one and this one. Okay. Now you do a quadratic approximation. So you consider this is equal to nabla phi of y dot x minus y plus order of the second derivative times x minus y square. Okay. And again, this second derivative term more or less can be bounded by j times phi of some appropriate, okay, maybe some x or something. And again, from this term, you can pull out, in some sense, epsilon squared this time. Okay. Again, using the fact that Gaussian is much smaller once you are away by epsilon. Okay. So now this one is a little bit, you have to be a bit careful because you have the differentiation of this Gaussian, which produces more or less like 1 over epsilon. Okay, I don't want to go into this detail, but because of this term, you have this extra epsilon division, but since you have epsilon squared, that's okay. Okay, so very roughly speaking, this term can be handled. Okay, so the point is, you can replace this phi x by, so you can replace phi x by roughly phi y plus nabla phi y dot x minus y. Okay, so I hope that. Now, so you look at the difference. Okay, so now look at the a plus b. So taking these into account, let's see. So note first of all, replacing this by y. Cancels this one, right? Okay. This phi x, if you replace by phi y, you have a minus sign there, so it goes 0. Okay. So you're left with this nabla phi of x minus y and also this term. Okay, so now you write this out. Yeah, you write out this one, dropping this term comes out to be k ij ex gamma ij, and you will find that this is equal to phi. Let's see. Maybe I'll just write out everything. Yeah, I hope that somebody smart can tell me why this works. In fact, x minus y d phi d yl. If you diligently write out what they are, comes out to be this, I think. Just a moment. Okay. That's strange. Something is wrong. Let's see. Okay. Okay, L, I guess we have a summation here too. And K is I guess that's correct, yeah. Please let me know. It's so strange. Let's see. IK. There's of course K. Yeah, I just replaced this guy, which is this one. Nabla phi dot x minus y is this one. And we only left with this one. D phi dxk. But I changed it to y. Yeah, d phi dy. And okay. I hope this is this fine. Yeah, this one. Yeah, I just dropped already. I dropped. Right. Sorry. Yeah, I guess with some. Yeah, that's right. Yeah. So here I'm kind of dropping this as something that's less harmful. Yeah. Okay. So now this part is a key to the next step. This part, just carefully looking at this, you can write this as d dxk and d phi dyl. And yeah, you can write like this. It's a bit strange, but first, that's okay, right? It's differentiating this gives you yeah. Yeah, I hope this is correct. Yeah, so yeah, if differentiating this guy gives you this term, right? Because when x is equal to L, k is equal to L, you have this guy, right? And differentiating this gives you this one. Okay. I hope that's fine. So now note that this can be, so one thing you notice, this quantity is that, you see, this is where Gaussian is important. This x, this YL of psi, well, it's like a bit like Fourier transform, but it's since it's a Gaussian, actually, it comes out to be this. Plus exponentially small term. Okay. So we have a cutoff function, so that part is exponentially small, but otherwise, if you differentiate Gaussian, you have this come out as a factor from the exponential factor, right? So actually, you can replace this by, well, okay, so exponentially small term, you just drop out. It's small. We can handle this. Okay, so just forget that one. So using this really crucial property of the Gaussian, you can actually change this to. By the way, also you can, y doesn't matter so much. So just let this out, and the d dxk and d dyl of phi. Sorry, times epsilon square. Here's important. Epsilon square. So you can prove out this epsilon square. That's very important somehow. You can prove out this epsilon square. So we can play with this one now. Okay. So now, so this difference become now with this epsilon square at hand. And you can write like this. You can rewrite the formula like this, because you replace this part by this, and basically what you did is, I guess you change the order of this differentiation, okay, which gives you this one, and the y differentiation, has nothing to do with this integration, so you can take this outside. A little bit like magic, but you can do this. I hope that's clear. This, that, and then just change the order of differentiation. Take out y outside, and then you're left with this one. Okay. Yeah. So that's I hope it's clear. Now is something very nice. You notice that this is nothing but just minus h tilde from gamma I times epsilon plus this. Okay. So, by definition, this is precisely this one. That's how you define this, right? Very nice things about this is that you have this sort of differentiation of but h this times this. So actually you can do integration by parts. So you see, I hope that's clear. Yeah, you see this falling onto this one is the one that you can do integration by parts. And so you can actually do integration by parts. To get, so I'm using the fact that you see here is a same guy, here is same guy, so more like you can interpret this as d dy L of hi to the square. Okay, so you can pull out this guy to do integration by parts. So this comes out to be, and the bonus is really having this epsilon square. That's very important because you can make everything small, using this epsilon square. So this gets you to integrate by parts, epsilon square, Rn plus 1, and here's a minus d phi. I think if you compute, you can see. Yeah, it's a bit messy, but the idea is that you don't have to differentiate this h. That's the most important thing. It's a bit messy, yeah, but key point is the fact that you can do integration by parts. Analysis, of course, everybody knows that if you can do integration by parts, you're sort of winner. So, yeah, so here's something you can do. And so note that here is this term. And actually, you can prove that this guy is not so bad. It's actually of the order of 1 over epsilon. Okay, so I don't want to go into this much. So, and also this, you can bound this by j times phi and stuff like that. And so you can still have epsilon square, so you still have, epsilon. Yeah. And then j you have, but j is much smaller than, j times epsilon is much smaller than like 1 over epsilon to the 1 quarter, for example. Yeah. So differentiation of this is not a problem. And also this also too, in some sense, differentiation of this and differentiation of this, or you can bound it by either this type of quantity or this one is like 1 over epsilon. Okay, so because of that, you can bound this guy basically like by epsilon to the 1 over 4th and this quantity, basically h to the square. This type of you can bound this type of quantity. Okay, so but the key point is this little trick here. The fact that this Gaussian has this property. Again, as I said, it's like a little bit like a Fourier transform type of sort of feeling that you see differentiation become a sort of product in some sense here, right? This variable become a differentiation, basically. So in some way, certain kind of symmetry is at play, I think. But so that's more or less the proof. And again, as I said, this lemma is the most probably the key estimate that this scheme works, because otherwise, I don't know how to at the end prove Brakke's inequality, because as I said, this formula tells you. This formula tells you this. This part tells you how the surface area changes locally. Okay? Locally. You need to know that to get a Brakke's inequality. Not a total surface area, but locally. And that's actually given by this precisely. So you do have a very good handle on this change of the surface area in this way. Okay, so today it's over. Thanks.